started on finishing off section 3.3, trig derivatives. I want to go over how do you find the equation of a tangent line and how do you find multiple derivatives. We really don't have any new stuff because we know how to do both these things. All we're doing it is, well, we're going to be doing it with trig functions. That's pretty much it. So I'm finding one as we speak, and this is question 16. And we're being asked to find the equation to the curve e to the x cosine x plus sine of x at the point 0, 1. Right. So we're being asked to find the equation of the tangent line to this curve at that point. And just like every other equation of tangent line question, it really falls into two stages. Step one, find the derivative at 0, because that will give you the slope, right, the m for your tangent line. And then use the y minus y1 formula to get the equation. So, looking at this one, would you agree that this is a product rule for the first bit? And plus sine x, when you differentiate it, just gives you plus cosine x. We happy with that? So product rule plus the derivative of this guy. Now, for the product rule, we have differentiate e to the x, leave the second guy alone, leave the first guy alone, and if you differentiate cosine, you get negative sine of x plus a cosine of x. Try and make it look a little bit prettier. Not much really. E to the cosine x, take away e to the x sine x plus cosine x. So that is the derivative. I'm now going to find the derivative at the x coordinate of 0. And that's going to be the slope of our tangent line. So it's going to be e to the 0, cosine of 0, take away e to the 0, sine of 0, plus the cosine of 0. What number is the cosine of 0?
It's 1.
Yeah. And isn't e to the 0 also 1? So what do I get here? I basically get a 1 times 1. E to the 0 is 1, the sine of 0 is 0, so here I get 1 times 0, plus the cosine of 0, which is 1. 1 times 1 is 1, that's nothing, add another 1, we got 2. We now know the slope of the tangent line is 2, at least at that point. Right, so that's stage 1. Find the derivative, evaluate it at whatever this is, x coordinate is, and that will give me the slope of the tangent line. I then do the y minus y1 bit. It's called the point slope equation to find the equation, the tangent line. And so what's it going to be? It's going to be y take away 1 equals 2, x take away nothing. So y take away 1 is 2x. So y is 2x add 1. And there's the equation of the tangent line. We are finished. That's kind of cool, right? Pretty straightforward. What can go wrong? Well, not too much, as long as the function's not horrendously ugly. The value of x that you use on a trig function, you have to know standard angles. I want you to imagine that it wasn't at 0, 1, but it was at pi upon 3, 2. Now, when you get angles that are pi upon 3, or pi upon 4, or pi upon 6, right? So imagine we had those kind of questions. You're going to have to find the sine of pi upon 3. You're going to have to find things like the cosine of pi upon 4. You know, it depends what the function is, right? You might have to find the tan of pi upon 6. In other words, you will need to bring back your knowledge from trig of the sines, cosines, and tangents of standard angles, right? These are called standard angles. One way to do that is to memorize this little triangle. It's the 1, 2, root 3 triangle, right? It's almost like 1, 2, 3. It's 1, 2, root 3. Now, what this triangle allows us to do is to find sines, cosines, and tangents of any of these two, the outside ones. So, for instance, if I wanted to find the sine of pi upon 3, the sine is opposite over hypotenuse. So the answer would be root 3 upon 2. If I wanted to know the tangent of pi upon 6, right, here's the tangent, it's up here. The tangent is opposite over adjacent. So this would be 1 over root 3, and then you could make it look pretty. If you want to do the pi upon 4 one, there's a triangle for that guy as well. And it's the 1, 1, root 2 triangle. And if you wanted to know the cosine, it'd be 1 over root 2, which you can then tidy up. So you can either memorize these two triangles, or you can have your unit circle handy and have that one memorized, or whatever. But can you imagine that in some circumstances, it's not just going to be the cosine of 0 or the sine of pi upon 2. Those ones you don't need to memorize, you could get them in your calculator, right? The answer's 0 or 1, mostly, right? You got to do the pi upon 3s and the pi upon 4s occasionally as well. Are we good with the equation of the tangent line process? Because we've done it in other circumstances. So I'm not really changing the process. Find the derivative, evaluate it at this number 0, and then use the point slope equation. We're good? So now we're going to look at the second theme to finish this off, and that is we're going to look at finding first and second derivatives. Technically, I'm not going to do it, but couldn't you find third, fourth, and fifth if you wanted to? So let's have a function. And the guy I'm going to do is sine x cosine x plus x squared, right? And we would like to find the sine, not sine, the first and the second derivative of this function. So I'm going to do a product rule. Let's see what we get here. It's going to be f dash g plus f of g dashed, and the derivative of that guy is just 2x. So it's going to be cosine x times cosine x plus sine x times negative sine x plus 2x. And this is going to be cos squared x, take away sine squared x plus 2x. What's cos squared x take away sine squared x? It's one of those guys, the double angle guy. Can you remember who he is?
Cosine 2x?
Sine 2x plus 2x. Now, if I had to find the second derivative, well, I know how to find the second derivative of this guy. It's just 2. Don't have a problem with the derivative of the cosine of 2x. Because I don't know what the derivative of cosine 2x is. I could have a guess. It'd actually be wrong. At least my guess would be wrong. I might think it's negative sine of 2x or something, and it isn't. So we need to find the derivative of things like the cosine of 2x, don't we? Which is our next section. I'm going to show you a new rule. It's called the chain rule. And it will allow us to differentiate things like the cosine of 2x. In fact, it will allow us to differentiate much uglier things than that. So who is the chain rule? Can you remember in 141 doing things called fogs and goths and gogs, right? Composition of functions. Functions of functions, essentially. You remember those guys? The chain rule is a rule that allows us to differentiate those kinds of functions. And so let's show you what it looks like. If I have a function y and it's made up of this guy, basically fog of x, f of g of x, then the chain rule tells me its derivative. It's f dashed of g of x times g dashed of x. And that is called the chain rule. That guy is a very useful rule. It allows us to expand things that we can differentiate. Now, it's quite different in a lot of respects from the product and the quotient rule. And the product and quotient rule, like plug and chug, right? You put f here, you put g dash there, right? You put things in. It is a real formula. We do not use this formula at all. What I want you to think of is that this is actually just describing the process, because the chain rule is a process rather than a formula that you use, rather than a rule. So let's jump right in and show you how it would work. Suppose I wanted to differentiate that function. Well, we've got a big problem here. The only strategies we've got are impractical. Strategy number one is FOIL that thing out. You are never, ever going to be able to pay me enough money to FOIL that out. Could you imagine how big that would look? It would be 2 pieces of paper and some. And once it's FOILed out, wouldn't I just have things like x to the 200 and some other things, right? Lots and lots of them. And then I would have to differentiate every single one of them, and there'd be about 100 different things. And that would take some time. And that's me not finished. When I've got that all done, shouldn't I use style points, which means factor it all back together again? Now, if you think factoring a quadratic is difficult, how hard do you think it would be to factor a polynomial that was x to the 200 and all the way down to plus 3 to the billion, right? You'd be there to Christmas and some and still never do it. So that's off the list. The other way is, couldn't I write that down as x squared plus 3 times x squared plus 3 times x squared plus 3 100 times? And couldn't I do the product rule with 100 pieces to it? Would you agree that's just ugly in a different way? It would be horrendously hard. And even at the end of it, I'm not sure you'd get it right. So those are off the plate. So how do we apply this rule? Well, I want you to think of this not as x squared plus 3 anymore, but think of it as something to the power 100. And the guy that we call g of x is basically this guy here. He's the guy I like to use the word something. You're going to hear that word a lot today. This is something to the power 100. So according to the chain rule, its derivative is the derivative of that something times this guy. So here goes. The derivative of something to the 100 is 100 somethings to the power of 99 times the derivative of the something. Say it again. the derivative of something to the power of 100. 100 somethings to the power of 99, right? Just basically the power rule. Finishing off with the derivative of that something. Now, if you tidy it up a little bit, you get 200x, x squared plus 3 to the power of 99. Now, isn't there something nice and efficient about this rule? Let's do lots and lots and lots of practice at these. That way we'll get, I hope, more comfortable about it. Let's do a weird e to the power. I want e to the power of x squared plus 2x. I see that guy there, the guy I like to call something. That's the g of x they're talking about. So this is e to the something. So the derivative of e to the something is e to the something times the derivative of that something. And if I pull out a 2 as a common factor and rearrange the order, bingo. Now, hopefully, as I keep doing these guys, you'll begin to see it's a process rather than a formula, right? I'm not plugging things in. It's not really, that's not really a useful way to do things. There's a weird sine function. The sine of e to the x plus 2. That'd be a weird looking function. Let's find its derivative. Okay, who is the something in this case? Who's the g of x in this question?
E plus 2.
Okay, this guy here. Great. So when I look at this, I see the sine of something. If you differentiate the sine of something, you get the cosine of something times the derivative of the something. And normally we put the e first and the cosine second. Kind of cool. We'll do some the other way around. E to power of sine x. That's a pretty weird looking thing as well. Who's the something this time? Who is the g of x this time?
The sine of x.
Yeah. So e to the something, what's its derivative going to be? Well, the derivative of e to the something is e to the something times the derivative of that guy. And that looks pretty good. I'll leave that alone. Do you see how versatile the chain rule is and how different the things you use the chain rule on are? I mean, product rules kind of look like product rules, don't they? Two things multiplied. Maybe the two things are different looking, but they're two things multiplied. Have you noticed that when you do the chain rule, how quite different things look? But it's still the chain rule in every case. Okay, are we good so far? Are we beginning to get a feel for how this rule works? Have you also noticed I'm not really using that formula? I'm using things like somethings and derivatives of somethings. How about this rather innocuous, simple looking function? I'm going to do the chain rule on it, but I'm not going to leave it as that. Don't you have to call things fractional powers if you want to differentiate? And that's still true whether it's a chain rule or not. And the something here is going to be the 2x plus 1, agreed? So its derivative. Well, something to the power of half gets you 1/2 somethings to reduce the power by 1, followed by the derivative of the something, which in this case is just 2. And those two kind of cancel out, and this comes downstairs. And then this gets returned. So you know, still points are still in play, right? What am I doing here? Making it look like the original, aren't I, essentially? Let's look at this fella. What would be a better way to write this fella so I can start thinking about differentiating it?
Cosine x to the -2.
Agreed? -2. Now, something to the power of -2, right? This here is our g of x. This is our something. Well, if you have something to the power of -2 and you want to differentiate it, something to -2, -2 somethings to the -3 times the derivative of that something. And then to make it look pretty, you happy with the still points? Make it look like the original. Let's bring this guy back. Remember this fella that we kind of get stuck on? We're not going to be stuck on him now. Isn't he the cosine of something? Isn't our g of x just 2x? It's a cosine of something. Now, if you want to differentiate the cosine of something, don't you get negative the sine of something times the derivative of the something? So it's -2, the sine of 2x, add 2. There, we've now finished that question. So the cosine of 2x is the cosine of something. Well, what's left? Well, we've got a lot left, a lot to do. But the more practice we get, hopefully, the easier when you look at these things for you to say, oh, I remember, I've seen something like that before. Or at least you know it's a chain rule, and you can, and if it's the first time you've seen this particular situation, you can still work your way through it. So I'm going to look at, here are some examples. I would like to differentiate e to the power of x squared times the cosine of x cubed. Now, since these are two things multiplied together, that tells me I'm going to be using the product rule. Right? The product rule doesn't go away just because we know a new rule. Right? So this is two things multiplied together. What makes this a little bit different? Aren't the two things that we're going to multiply, don't both of them need the chain rule? Right? That's the e to the something, and that's the cosine of something. Now, when questions get complicated, where you're doing a product rule with chain rules inside it kind of thing, I find it helpful to go over here and write down who the f and the g are and their derivatives. Because once I know what these guys are, can't I just plug them in here and I'm finished? Right. So the first guy is e to the x squared. So e to the something. Differentiate e to the something, you get e to the something times another 2x. That's that one done. Cosine of x cubed. Well, that's a cosine of something. You differentiate a cosine of something, you get negative the sine of something times the derivative of that something. So now I can put all the pieces together. F dashed, which is this guy, times g plus f, and g dashed is this fella. Actually, there's a negative floating around, but I'll put it here. Tidying up a little bit, 2x e to the x squared cosine x cubed, negative 3x squared e to the x squared sine x cubed. And that's kind of where we are right now. You always have to do style points. Look at these two expressions. Is there any decent tidying up we could do?
Factor out an xex squared.
Agreed. And what does that leave me with? It leaves me two of these guys. Take away 3x of this guy. And now we've done our first example of a product rule that used chain rules. Right? So my next question is going to be a quotient rule that has chain rules in it. So here is a fraction function, right? A quotient rule. Top is f, bottom is g. Its derivative is going to be f dashed g, take away f of g dashed, all over g squared. The top function is that guy. And the one on the bottom is that guy. So when they get messy like this, I'll do my usual split it into smaller jobs. This is the top. The plus x just gets me a plus 1. So the sine of something squared, right? We've seen things like that, right? Sine of something squared, cos of something, right? Cos of something, and times the derivative of something. And this guy, negative the sine of something, times the derivative of the something, and the one doesn't give me anything at all. So f dashed, I'll tidy it up while I'm writing it, is 2 cosine cos of x squared plus 1 times cos of x squared plus 1. Yeah. Don't have room. Take away the untouched top guy, which is that, times the derivative of this fella, which is negative 2x, the sine of x squared, all over the cosine of x squared plus 1. I should have thought this one out before I picked it. It is ugly, 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 ugly. I'm not even sure I'm going to get much out of this. So I'm just going to say dot, 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 dot over the cos of x squared plus 1 squared. And what's dot, dot, dot going to be? Can you imagine foiling all this out and multiplying this out, and probably nothing will kill anything off, and you just have one horrendous ugly top. But it's doable, isn't it? I mean, you could finish it off, it just take too long. So a quotient rule, and this isn't the only quotient rule you'll see, because I'm doing them tomorrow, so I'll probably look at a homework question next time. So that's the process for product rule. This is the process for a quotient rule. So who is the combination I haven't done? How about a chain rule with a chain rule in it? Y equals. Yeah. Something to the power of 10 doesn't look too bad. 10 somethings to the power of 9 times the derivative of that something. I'm just writing down in English what I'm doing. So what's that get me? It gets 10 lots of this. And what's the derivative of e to the 2x plus 1? Well, it's e to the 2x times something. Because isn't e to the 2x a chain rule? Right? It's not e to the x, it's e to the 2x. So it's e to the something, right? So the derivative of e to the something is e to the something times a 2. Do you see where that extra 2 is coming from? The derivative of e to the 2x is e to the 2x times 2. Not an awful lot you can do to make this pretty, so I'm not going to. Now that was a very short version of a chain rule with a chain rule. Try another one. Sine of x cubed plus x all raised to the power of 5. That is also a chain rule inside the chain rule. This is my something. So my first layer, it's like, you know those Russian dolls where you have a doll inside a doll inside a doll? It's kind of like that analogy. So this is the outer doll, something to the power of 5. Then you get 5 somethings to the power of 4 times the derivative of that something. So you get 5 of these guys. Now, what's the derivative of sine x cubed plus x? Well, the plus x is easy, right? That's plus 1. Isn't the sine of x cubed its own little chain rule, right? It's a sine of something. So when I differentiate the sine of x cubed, won't I get the cosine of x cubed times the derivative of it, which is that guy? So you see that's like the doll inside the doll. Now, to try and make this pretty, there isn't really anything much to do. And I'm really just shuffling the cards here, you know, putting them in a slightly different order. And that's the answer to the derivative of that function. Do you see how versatile the chain rule is? What it's allowing us to do is to add another dimension to what we can differentiate. We can now differentiate some weird and wonky looking functions. I mean, e to the power of sine x, what the heck would that look like, right? But we can differentiate it now. I kind of like this question. I've already given it to the other class. You're getting yours a little bit early because I've got another one after this. But this is Elizabeth O'Neill's puzzle question. E to the power of e to the power of e to the x. I gave them 30 seconds because I didn't have a lot of time. I'm giving you a minute. Figure out who that guy is. That's got a lot of Russian dolls in it. The last few seconds. The answer is kind of got a nice symmetry to it. You just have to keep your eye on who the something is because it keeps changing each time you move the doll towards the center. So e to the something gets you e to the something times the derivative of the something, right? So you have this guy. Now, e to the something gets you e to the something times the derivative of that something. And now you get can you kind of see the doll inside the doll inside the doll thing? Chain rules inside further chain rules.
Find the exponents, right?
Exponents. Yeah. E to the E to the X kind of thing. Our last one for today. Looks like a chain rule, right? Looks like a quotient rule. Looks like it's got a bit of A and a bit of B, right? A bit of each. Does the chain rule come first and the quotient rule later? Or is it a quotient rule first and a chain rule later? Because the order you do it is just as important as what you do. Which comes first? Chain rule or the quotient rule? What do I do first? No takers?
Oh shit.
Because you see the fraction? That's good. I don't mind having a shot. So if I say no to you, Skylar, that's not the first one, then by implication, it's the other one. So what makes that different is, can you see this is really something cubed? So when I look at it as something cubed, I see a chain rule first, which means that the answer is 3 times something squared times the derivative of that something. I sometimes find it helpful, for me anyway, to actually write this step in rather than just say it in my head and try and do it. Because now, don't I have a different job to do? Don't I just have to find the derivative of a quotient? Right, this thing here. So what do I have? I have 3 lots of this guy squared. This fella here is just a normal quotient rule, right? Doesn't need a chain rule. It's just a normal quotient rule. It's going to be f dash g, take away f of g dashed, all over g squared. This is the last question for today. Now, if you differentiate the top, you get 2u, leave the other guy alone. Take away, leave the top alone, differentiate the bottom, and the whole thing in the bottom, just the bottom, gets squared. What do I get? 2u cubed, 2u cubed, take away 2u, take away 2u cubed, take away 2u over this guy. Almost there. Kill, kill, combine. And that's kind of where we are right now. Okay, that thing there came out relatively pretty, right? Style points. I can do better than just combine the 3 and 4 and call it -12. I can do better. But I have to be aware that just because something is written one way doesn't mean that I can't break it apart and write it a different way. So I'm going to have -12. I'm going to have u squared minus 1 cubed. One of these is a plus, by the way. There we go. Over u squared minus 1 and another u squared minus 1 squared. So what did I do there? Well, the 3 and the 4 get me -12. I split this as a u squared plus 1 cubed on the top and a u squared minus 1 cubed on the bottom. And for the time being, I left this alone. But do you notice I can now combine the top guys? Sorry, the bottom guys. There. Would you agree that's a little bit more elegant than what it was a couple of lines back? So in this particular question, the style points was a little bit unusual, but nonetheless, it had to be done. There is a temptation, I can understand it, that when you see this, that you think that says like carved in stone, you can't undo it. No, can't you break it apart if you feel it's helpful? If this guy over here had nothing to do with that guy, I probably wouldn't have broke it apart. I would have left it alone. But because I noticed that the bottom and this were the same, I thought there'd be a benefit of breaking apart, and there was. Okay, say hi.